Good morning, friends. Last we discussed about the characteristic of photoelectric effect and also Einstein's explanation about the photoelectric effect. We derived the question of the maximum kinetic energy of the emitted photoelectrons half m v square maximum is equal to hf minus phi. Phi is the wave function. Clear? That means we discuss in photoelectric effect the light behaves as a particle nature. Because when the light is incident on a metallic surface, the absorption and emission of the energy take place by considering the particle nature of a light. That is explained by the Einstein. Now, today we are going to discuss about the dual nature of light. And before that, the particle nature of the light, that means the photon. Can the quantum of light be associated with particle? Actually, that is for our knowledge and also for short question. There is not asked in board exam, but to clear a concept about the particle and wave nature of a light, we are discussing about that which effect or the which phenomena can be explained by considering the light as a particle or the light as a wave. So question is that can quantum of light can be associated with particle? Already we discussed in Einstein's explanation. The quantum of light or the packet of energy of light, that is known as the quantum or the quanta, and that is known as the photon. So photon can be associated with a particle. So for the answer of this question, the photoelectric effect gave one unusual fact that when the light impacts with matter, it behaves as if it is made up of the discrete quantum. Energy of each quantum is hf. So in photoelectric effect, give the unusual fact that when the light is incident on a metallic surface, the absorption of energy takes place in discrete units. This discrete unit is known as the quantum, and that is the photon. So according to Einstein's explanation, not only the emission but the absorption of energy takes place in discrete unit, and this discrete unit of energy is known as the quantum. Having the energy hf, f is the frequency of the light. So there are the two evidence that the light can be evidence with particle. Again, in photoelectric effect we discussed about that when the light is incident on a metallic surface, so the energy is absorbed by the electron. So absorption process takes place in discrete unit of energy, and this discrete unit of energy is known as the quantum or the quanta, and that is known as the photon, and that represents the particle nature of a light. Right? There are the two evidence that the light can be associated with the particle. Here the two evidence the light can be considered as a particle. One is Einstein declared that the quantum of the light has the momentum of hf on c. So earlier in explanation of the Einstein shows that, or the Einstein also proved that the absorption and emission of the energy take place as a quanta of energy having the energy hf. Right? Therefore, f is the frequency. After that, the Einstein also derived that the quantum of the light has the momentum. Momentum of quantum is hf upon c. Here the h is the Planck's constant, f is the frequency of light, and c is speed of a light. Right? Thus the quantum of the light has the energy of hf, and momentum is hf upon c. Already we discussed in classical mechanics about the energy and momentum. Momentum P is equal to mass into velocity. Mass into velocity. That represents the particle. So here the quantum of energy also has the momentum. So we can consider that the light also behave as a particle because it possesses the momentum. And due to that, thus the quantum of the light has the energy of hf and the momentum of hf upon c. Hence the quantum of the light can be associated with a particle. And this quantum of energy is known as the photon. It is known as photon. Now the second evidence is given by the other scientist named as the quantum. So other evidence to associate the light quantum with the particle nature was given by the scientist Compton in 1924. He made the experiment of scattering of X-ray by using the electron. So when the Compton, name of the scientist, performed the experiment of the scattering of X-ray, at the time they used the electron. Electron is the particle nature of the light. Therefore, the photoelectric effect in quantum effect gives the evidence about the light behave as a particle. Clear this? Again, the two evidence. One evidence is that Einstein derived that the quantum of light has the energy hf and momentum is hf upon c. Here the h is the Planck's constant, f is the frequency of the light, and c is the speed of the light. And hence the quantum of the light can be associated with particle. And this quantum of energy that is known as the photon. Other evidence to associate the light of the quantum with particle is that given by the scientist known as the Compton in 1924. He made the experiment of scattering of X-ray by using the electrons. So these two effects, photoelectric effect and quantum effect, represents the particle nature of the light. After that, the dual nature of light explain the particle and wave dual nature of matter. So optical phenomena like as the interference, diffraction and polarization can be explained by the wave nature of the light. Yeah, even by that, the interference, diffraction and polarization. These three phenomena can be explained by considering the light behave as a wave. While the photoelectric and quantum effect can be explained by considering the light is behave as a particle. So here, in some effect, the wave nature of the light is important, and for some effect to explain the particle nature of light is important. Now, thus when the light is in motion, that means the light is propagated in the medium, it behaves as a wave. It behaves as a wave. And its absorption and emission take place in form of particle. Again, when the light is traveling, is in motion, at that time it behaves as a wave. While the absorption or the emission of the light take place in form of a particle. Take place in form of a particle. Therefore, at the same time, both nature of light is shown. Now, thus the light possesses the dual nature. Now, the one more example by our naked eye. When we see an object by our eye, both natures are important. When we see the object during the daytime, the colorful picture, the colorful object are shown, but the same object shown during the night. At that time, this object is not colorful. For that purpose, the two cells, lower and cone cell, are important to form the picture on the retina of our eye. For that purpose, when we see an object by our eye, both natures are important. Okay. The gathering and focusing of light by eye lens is described in wave nature. So when we are observing the close object or the far object, at that time, the light gathering and focusing power of a lens, there is represents the wave nature of light. Right? The absorption of light by the cone of the rod cell or retina requires the particle nature of light. During the daytime, the color picture is obtained, and during the night, the black and white or the black pictures of black object is shown. That is due to the absorption of the light by cone and rod cells of our eye or head. So that requires the particle nature. Therefore, in our daily life, both nature of the light are important, the particle nature and also the wave nature. Here it is, so there is the dual nature and there is the particle nature. The particle nature of light can be explained by the photoelectric effect and quantum effect, while the wave nature of the light can be explained by interference, diffraction and polarization. Thus, the conclusion is that light behaves as the particle and also as a wave. When the light is in motion, it behaves as a wave, and when the absorption or the emission of the energy take place or the light take place, at that time the wave nature is required. Clear this? Okay. Okay, now what are the characteristics of photon? Already we discussed about that photon is the bunch of energy, that means the discrete unit of energy that is known as quantum or the quanta or the photon. And we also discussed in Einstein's explanation, the photon produces the energy is equal to hf and momentum is hf upon c. Now this question is most important, frequently asked for 2 marks. Write any 4 characteristics of photon, or write the characteristic of photon. Okay. Now photon is the particle nature of a wave. Right? The photoelectric and quantum effect characteristic of photon are represented as follows. So here, what is the behavior of photon? Or how we describe the photon? So that can be explained from this characteristic. Here, the photoelectric and quantum effect represents the particle nature of a light. That means the absorption and emission of energy take place in discrete unit of energy, that is the photon. Now the first characteristic is that during interaction and radiation with matter, radiation behaves as a particle that is known as photon. Now listen again, during interaction and radiation with matter, radiation behaves as a particle, and this particle is known as the photon. Now the second, energy of each photon is hf and momentum is hf upon c. Again, the energy of each photon is hf and momentum is p is equal to hf upon c. F is the frequency of radiation, h is the Planck's constant, and c is the speed of light in vacuum. Okay. Now, third characteristic, in vacuum, the speed of photon is equal to the speed of light. Again, the speed of photon in vacuum is same as the speed of light in vacuum. That means the photon traveling with the same speed of light in vacuum. Now, if lambda is the wavelength and f is the frequency of radiation, then energy of each photon is equal to hf and momentum of each photon is p is equal to hf upon c. But we know that c is equal to f lambda. Right? Therefore, f upon c is equal to 1 upon lambda. Here I substitute the value of f upon c. So that is the 1 upon lambda. Therefore, momentum p is equal to h upon lambda. Actually, this equation represents the dual nature of radiation or the matter, that means the particle nature and wave nature we discussed later. Right? Again, what is the first? During the interaction and radiation with matter, the radiation we have as a particle that is known as the photon. Interaction, that means when the light is incident on a particle, at that time the energy is absorbed. And radiation, that means the energy is emitted from the metal or the initial phase take place in form of a discrete unit of energy that is known as the photon. Now, energy of each photon is hf and momentum is hf upon c. In vacuum, the speed of photon is equal to the speed of light. And fourth characteristic is same as the second. If lambda is the wavelength and f is the frequency of radiation, the energy of each photon is capital E is equal to hf and momentum P is equal to hf upon c or h upon lambda, because from this equation C is equal to f lambda, therefore f upon c is equal to 1 upon lambda, therefore momentum P is equal to h upon lambda. Now fifth characteristic, according to the photon theory, if n photons are incident on unit area, then intensity of the light I is equal to nhf. Again, already we discussed about the intensity of a light or the radiation. Intensity, that means the energy incident on unit area in unit time. That is known as the intensity. Right? So according to the photon theory, if n photons are incident on unit area, then intensity of the light I is equal to nhf. Hf is the energy of one photon. Here the n photons are incident in unit area, therefore the total energy incident on unit area, that is the intensity I is equal to nhf. Hf is the energy of photon, single photon or the one photon. Therefore the energy of the photon does not depend on intensity of incident radiation. Again, the energy of the photon does not depend on the intensity of incident radiation. Okay, now 6. Photons are electrically neutral. They do not get affected by or deflected by electric or magnetic field. Photons are electrically neutral. Therefore, the effect of the electric and magnetic field does not deflect the electron from its path, photon from its path. Okay. And seventh characteristic is during photon particle collision, the total energy and total momentum are conserved. Clear? Again, the fifth. According to the photon theory, if n photons are incident per unit area, then the intensity of light I is equal to nhf. hf is energy of each photon or the one photon. Therefore, the energy of the photon does not depend on intensity of the radiation. Now next, photons are electrically neutral. They do not get deflected by electric or magnetic field. And seventh is, during the photon particle collision, the law of conservation of energy and law of conservation of momentum is fulfilled, or in other words, the total energy and total momentum is conserved. Sometimes the conservation of number of photons may not be take place and new photons may be produced. But in our characteristic, here the total energy and total momentum are conserved during the photon particle collision. And eighth is the mass of the photon is represented by n is equal to hf upon c square. How we obtain it? According to the Einstein's theory, E is equal to mc square. But just read here the equation of the energy of the photon is hf. hf is equal to mc square, therefore m is equal to hf upon c square. Therefore the energy of the photon is E is equal to hf, momentum P is equal to hf upon c, or the h upon lambda, and mass of the photon is hf upon c square. Clear? So these are the characteristics of photon. These are most important for 2 marks question. Now the next question is the de Broglie's hypothesis. Already we discussed about the dual nature of light or the radiation. In some circumstances the light behaves as a particle, while in some circumstances the light behaves as a wave. Now already we discussed about that when the light is in motion, at that time the wave nature of the light is considered, and when the light is incident or the impact on a matter, at that time the absorption and emission of the light take place in particle form. Right? Therefore, the de Broglie suggested the hypothesis and derived the mathematical relation between the both nature of a light, particle and wave nature. So the question is that explain de Broglie's hypothesis or the right de Broglie's hypothesis and derive the equation of de Broglie's wave. For that purpose, the hypothesis is that the moving particle of matter should display wave-like properties under the suitable condition. That means when the particle of matter is moving, at that time represent the wave-like property under suitable condition. So that is the de Broglie's hypothesis. Okay. The nature is symmetric and two basic physical quantities, matter and energy, must have the symmetric character. So in nature, the two basic physical quantity, like as the matter and energy, that means the mass energy relation, must have the symmetric character. And this type of the relation is given by the Einstein E is equal to mc square. Okay. Now, if radiation shows the dual nature, then the matter also possesses the dual nature. Again, according to the the de Broglie's hypothesis, the moving particle of the matter should display the wave-like properties. Under suitable condition, this statement is the de Broglie's hypothesis. Now, nature is symmetric and two physical quantity, like as the matter and energy, must have the symmetric character. If the radiation shows the dual nature, then matter also possesses the dual nature. Radiation shows the dual nature, therefore the matter also possesses the dual nature. De Broglie shows that the wavelength of the particle is lambda and momentum is p. Therefore, lambda is equal to h upon p. But we know that the momentum of a particle p is equal to mass into velocity. Therefore, lambda is equal to h upon m. Right? Again, the de Broglie shows that the wavelength of particle is lambda and momentum is p. Therefore, lambda is equal to h upon p. P is the momentum of a particle having mass m and speed is v. Therefore, h upon mv, that is equation 1, where the m is the mass of the particle and v is the speed of a particle. From this equation, the de Broglie's equation, the dual nature of the matter can be observed. So this equation 1, lambda is equal to h upon p or lambda is equal to h upon mv. That shows the relation between the particle and wave nature of a light. So in equation 1, lambda is the wavelength associated with the wave nature, and p is the momentum associated with particle nature of matter. Thus, the equation 1 shows the dual nature of matter, particle as well as the wave nature. This hypothesis for particle of matter, it is also true for photon. Now, from this equation, the photon has the momentum p is equal to hc upon lambda. P is equal to hc upon hf upon c. Again, this hypothesis for the particle of matter, it is also true for photon. Now, the momentum of photon p is equal to hf upon c. Now we know that the c is equal to f lambda. C is equal to F lambda, therefore C upon F is equal to lambda. Therefore, this equation C upon F is equal to H upon P. Therefore, lambda is equal to H upon. There is a same equation 1 for the photon, that is known as the de Broglie's wavelength. So that is the important equation frequently we are using in objective type question and also the numerical to find out the wavelength of a particle. Right? Lambda is equal to H upon P. P is the momentum of a particle. Particle possesses the mass m and speed v. Therefore, lambda is equal to H upon m. Now, thus the de Broglie's wavelength of photon can be associated with wavelength of electromagnetic wave. Thus, the photon of radiation possesses the quantum of energy and momentum. Again, the de Broglie's wavelength of photon can be associated with the wavelength of electromagnetic waves. And thus, the photon of radiation possesses the quantum of energy and momentum. So that is the de Broglie's hypothesis and de Broglie's wavelength. The equation of the de Broglie's wavelength, lambda is equal to H upon P or H upon M. That equation represents the dual nature of matter, particle and also the wave. Clear?